When examining this orchestral simulation implemented with Tone.js, one must first appreciate the architecture and data structures underlying the system. At its core, the code organizes musical information into a structured JavaScript object called Orchestra data, which defines the instruments, their available notes, melody pools, and chord pools. This structure is essential because it allows the orchestral logic to reference specific notes, organize them into motifs, and dynamically select chords for harmonic coherence. Each instrument is initialized as an instance with properties not only representing the sampler, notes, and pools, but also tracking state variables such as is active, is playing, solo, last note, last motif, and note usage. These state variables are critical for creating meaningful randomness. They ensure that notes are not repeated excessively, motifs do not repeat immediately, and the overall musical output remains both varied and emotionally coherent. For teaching purposes, it is important to stress that this separation between data representation, notes, motifs, chords, and operational logic, playing, fading, motif generation, embodies a modular design principle, allowing instructors to point out how scalability is achieved when additional immense or more complex musical rules are introduced. The next fundamental concept to highlight is the use of weighted randomness and note selection. The weighted note function represents an elegant way to combine stochastic processes with musical constraints. By calculating the minimum usage count among all notes and restricting the candidate notes to those that have been used the least, the system achieves a balance between repetition and novelty. Further, by limiting candidate notes to a small interval distance from the previous note, the code ensures melodic smoothness, which is key to maintaining the calm and emotional character of the piece. This provides a perfect opportunity to discuss to students how randomness in digital music can be tempered by rule-based constraints to achieve desired aesthetic outcomes. One could expand upon this concept by introducing additional musical rules, such as voice-leading principles, modal constraints, or probabilistic weighting based on musical intervals and harmonic relationships. Another significant teaching point is the motif generation system. Each instrument has a motif pool which is dynamically filled by the generate motif function. Here, motifs are built by iteratively selecting notes and durations, applying optional ornaments, and occasionally inserting null notes to simulate silence or breathing within the musical texture. The pedagogical implication is that the code models musical phrasing and structure at a micro level. Students can see that motifs are not simply arbitrary sequences. They are small, repeatable, semi-randomized musical ideas that provide both rhythmic and melodic variation. This is an excellent place to introduce the idea of hierarchical musical structure in algorithmic composition. Motifs form the building blocks of sections, which in turn form larger temporal structures like movements or complete pieces. One could extend this discussion to concepts like motif transformation, inversion, retrograde, and augmentation, showing how these musical techniques can be algorithmically implemented in code. The orchestral execution is another rich area for exploration. Each motif is scheduled for playback using the schedule motif function, which combines dynamic timing, volume control, and fade-in, fade-out envelopes. Fade-in and fade-out are applied via tone gain objects, with durations randomized within specified ranges to simulate the natural swell and decay of acoustic instruments. This is crucial because it models expressivity beyond simply triggering notes. The system simulates temporal dynamics that are essential for conveying emotion. For students, this introduces the concept that digital music generation must consider more than pitch and rhythm. It must also model intensity, articulation, and temporal phrasing. From here, one could explore adding more sophisticated expressive parameters such as velocity curves, micro-timing shifts, or real-time modulation effects like vibrato and tremolo, deepening the pedagogical scope. Additionally, the orchestral planning and solo assignment system deserves careful explanation. The plan next composition function dynamically assigns solo roles and regenerates motifs for each instrument, ensuring that multiple instruments interact meaningfully and that solos occur without immediately repeating previous selections. This demonstrates the intersection between stochastic processes and musical design principles. Randomness is constrained to produce musically coherent outcomes. For students, this illustrates the importance of algorithmic orchestration. Even in a randomized system, certain musical priorities, such as balanced participation among instruments, solo prominence, and harmonic congruence, must be explicitly encoded. One could expand this concept by exploring adaptive orchestration algorithms that respond to real-time inputs, user interactions, or analytical models of musical tension and release. From a technical standpoint, the integration of Tone.js audio effects, including reverb, delay, chorus, and limiting, is an excellent opportunity to teach about signal chains and audio processing. Each effect contributes to the overall sonic atmosphere, creating a sense of space, depth, and calmness. Reverb simulates room characteristics and provides sustain, delay introduces subtle rhythmic echoes, and chorus adds a gentle modulation to enrich the sound. Limiting prevents clipping and ensures that the overall dynamic range remains controlled. This component of the code allows educators to bridge programming concepts with acoustic and psychoacoustic principles, explaining how digital audio effects can manipulate perception and emotional response. Furthermore, this can be expanded into lessons on effect routing, parallel processing, and the interaction between synthesis parameters and algorithmic composition. Finally, the user interface and interaction mechanisms demonstrate how programming, music, and pedagogy intersect. Users can toggle instruments, adjust tempo, and observe note usage statistics in real time, which makes the orchestral process transparent and pedagogically rich. From a teaching perspective, this is an excellent demonstration of how software design must integrate user experience with underlying algorithmic logic. The visualization of note usage, implemented with dynamically colored and sized spans, reinforces concepts of feedback, monitoring, and real-time data-driven insight into musical processes. This opens the door to discussions on interactive music systems, live coding performances, and user-centered design in computational creativity. In conclusion, the Calm Emotional Orchestra represents a rich intersection of algorithmic composition, probabilistic programming, digital signal processing, and pedagogical opportunity. It demonstrates the importance of modular design, constrained randomness, hierarchical musical structures, expressive timing, adaptive orchestration, audio processing, and interactive visualization. Each of these components can be expanded into deeper explorations. One could introduce machine learning to predict motifs, adaptive generative harmonies, dynamic user interaction systems, or even multi-layered orchestration strategies. The code exemplifies how technical programming concepts can be directly mapped to musical ideas, offering a highly fertile platform for instructing students not only in JavaScript and Tone.js but also in the fundamental principles of computational musicology, algorithmic creativity, and emotionally aware digital composition.